In this video, we demonstrate our visual analytics framework for analyzing transfer learning processes. The system consists of 4 views: the stat view, the instance view, the network relation view, and the feature view. After the dataset is loaded, the stat view is initialized with the accuracies of the source and target models. In the instance view, we can select one class or multiple classes to view the t-SNE projection result of all instances in the selected classes. The neuron similarity matrices and weight visualization can be enabled by selecting the class and the desired layers. At the same time, the feature view of the selected data is loaded as well. Users can explore the domain discriminability of neurons in the target model. In the first case study, we employ the Office 31 dataset with 31 categories of images. The pictures from the Amazon product profiles are used as the source dataset, and the photos from the webcam camera collection are considered the target dataset. After loading the dataset, the statistical measures of the source and target models are displayed in the stat view. In the accuracy chart, the source model performs well on the source dataset with high training and validation accuracies. However, the accuracy of the source model on the target dataset is around 0.4. For the target model, it performs significantly better than the source model on the target dataset, while it has slightly worse accuracy on the source dataset. In the class table, some classes receive the same high accuracies from both models, such as bike and calculator, while classes like file cabinet and phone have the most diverse performances between the two models. In the projection result of class bike, the images share similar characteristics such as visual angles and the appearance of the bikes. For file cabinet, the patterns of the cabinets in the different photos vary significantly. When selecting file cabinet and desktop computer, we find that the distribution of instances from the two classes are overlapped without a clear boundary, indicating a high chance of causing misclassification. When activating the first and second layers of bike in the network relation view, we see that the indices of the most important neurons are similar on both sides. Many of the source neurons with the same indices are also the most similar neuron of their target counterparts. The phenomenon still exists in deeper layers, such as layer 7. However, the proportion of the important target weights with corresponding important source weights are different between shallow layers and deep layers. In the weights between layers 6 and 7, the proportion is significantly lower. This issue also happens in the class file cabinet, where such a weight redistribution happens even in the weights between shallow layers, such as layer 2 and 3. In the feature view, the top 3 most domain discriminative neurons show flat ellipses. In the domain discriminability plot, the images show a wide range of tire shapes from circles to lines due to visual angles. Some low discriminability ranks depict patterns of handlebars and frames that exist in almost all images. We conduct another case study by exploring 2-digit recognition datasets, SVHN as source dataset and MNIST as the target. In the accuracy chart, the relationships between the lines from the source and the target models show a similar diverse trend to the first case. The models perform well on its own domain, but relatively bad on the other domain. In the class table, classes such as 0 and 1 receive high prediction accuracies on the target dataset from both models. However, there's a big difference between the two accuracy values in the class 8. When inspecting class 8 in the instance view, we find that the misclassified source instances are heavily blurred, and the misclassified target instances have irregular patterns such as extra long strokes, unnecessary big opening on the top, and cropped bottom circles. We activate class 8 in the network relation view. In layer 1, the extracted colors and patterns are slightly different between some target neurons and their most similar ones in the source model. The same situation happens in neuron 245, layer 7 in the target model. In layer 7, neuron 37 is used for extracting long freestyle curves and ranks in 5th place. However, its most similar counterpart receives a much lower ranking, rank 15, in the source model. In the feature view, the most domain-invariant features are used for extracting circular shapes, which widely exist in the number 8 in both domains.